In this video, we are going to look at systolic arrays, which are a certain kind of architecture that can be used for implementing regular kinds of computation that is performed in signal processing. In some ways, a systolic array is an extension of the core idea of pipelining. The assumption that we make over here is that we have some kind of a host processor and that we need to perform certain kind of computation. Now, that computation is performed on something that we call a processing element. And the idea is that we need to have some communication between the host and the processing element, some compute that happens on the processing element, and finally communication back to the host. Now, just as in the basic idea of pipelining, the time taken for the processing element is going to be the rate determining factor that determines the clock speed at which your system can operate, which means that we spend a certain amount of time communicating information to the processing element, some time computing, and then communicating the information back. Now, what if we were instead able to break up our computation such that I would communicate the data to a processing element, which would do a small amount of work, that in turn would pass on the information to another processing element, and so on. And finally, after the entire computation has been completed, we get the data back to the host. Now, what we can effectively say is that the rate determining step is going to be the time for any one of these computations, provided that we assume that each of the processing elements does more or less the same amount of work. Which means that, just like in the case of pipelining, if I can make the time required for an individual processing element smaller than the total computation time, I could in principle have each of these processing elements working on a different sample of input data at a different instant of time, and therefore the throughput, the overall throughput, even if not the latency, can increase. So in other words, the throughput can increase, but the latency will most probably remain the same. Or it may marginally increase, but that's not something that we are very concerned about. All right, so the question is, this is regular pipelining. What makes this a systolic array? The idea of a systolic array is when we further apply the restriction that each of these processing elements should be identical or close to identical. If they are identical, essentially what we end up with is something called a regular structure, meaning that a simple kind of processing element can be repeated again and again in order to get the overall computation working properly. This is the reason why these kind of structures are also called VLSI array processing structures, and are sometimes also known by the term systolic arrays. Now, why the term systolic? This refers to the analogy with how the heart works. We essentially have a system in the heart where the heart has a regular pumping action. On every beat of the heart, a certain amount of blood is pumped into the circulatory system. In the same way, we can think of the host in our case as being the heart of the system. On every tick of the clock, it pumps a new sample of data into the array of processing elements, which then propagates from one processing element to the other, and after a certain amount of computation, finally returns to the host. This analogy with the heart is useful in terms of just getting the basic description of the system across, but has no real purpose as far as the understanding or application of these kind of systems is concerned. We will use the term systolic arrays, but keep in mind that what we are primarily interested in is the array nature of processing structures and the regularity of the structure that we are using. Now, from the point of view of VLSI, what we will find is that when we are trying to do an overall layout, this array structure once again is very useful because I can create an array of identical or similar looking elements and have a very simple and regular form of communication between them. if I can have something of this sort, this is a regular structure which is good, as opposed to something which has one computation unit here, another one over here, another one somewhere else in another corner, and each of them needs to be connected through different kinds of wires. This is also possible, but ends up causing problems for routing of signals. Okay, so all of this is the motivational part, meaning that this is the background for why we might be interested in an array kind of structure, which has a certain regularity, which makes it easy to create VLSI layouts. And hopefully, if I can find a signal processing algorithm that can be mapped onto such a structure, I would be able to get high performance by using this kind of regular operating structure. The next question that we would be interested in is, what kind of applications can I look at, and how do I go about taking an application and mapping it onto this kind of regular structure? Most of the material that I'm going to be talking about over here is based on the book VLSI Digital Signal Processing by Professor Keshav Parhi. This book was published originally in 1999 by Wiley, but I believe it also has a revised edition from 2007 with some additional information. It's a very good reference for most of the material in this course, and in particular the material on systolic arrays is dealt with in a reasonable amount of detail over there. And the example that we will be following will be pretty much using the same approach. So the example that we are going to use is going to be a simple 3-tap finite impulse response filter. By definition, that essentially has a mathematical equation that says y of n is w0 into x of n plus w1 x of n minus 1 plus w2 x of n minus 2. The question is, now there are a certain number of computations that need to be done in order to generate each output value of y. And what we are going to do is to try and come up with something that we will call a dependence graph for these computations. And in particular, we are going to represent those dependencies by means of a kind of a lattice structure or a graph, so to say, which is plotted on a 2-dimensional XY coordinate system. What does this exactly mean? It's probably best explained by just going through the example over here. I'm assuming that I have two axes, I'll call them I and J, and the assumption that I'm going to make is each value of I, in other words I equal to 0, corresponds to the value x0, that is x of 0. I equal to 1 corresponds to x1, I equal to 2 corresponds to x2, x3, x4, and so on. Now similarly, on the vertical axis, I have my w's or weights. I'll consider j equal to 0 as w0, j equal to 1 as w1, and j equal to 2 as w2. Note that over here it's a 3-tap filter. I have only 3 weights, and therefore the entire computation, the entire list of weights basically stops there. In other words, on the vertical axis I have only 3 lines that I need to draw. Now let's look at this intersection point, I equal to 0, j equal to 0. If I assume that all the x of minus 1, x of minus 2, etc. are zeros, then effectively what I have is that this computation at this point w0 into x0 corresponds to the output y0. Similarly, I can look at w1x0 and w0x1. What I need to do is compute both of those, that is w1 into x0 plus w0 into x of 1, and the corresponding output is the value y of 1. Similarly, w2 into x0 plus w1 into x1 plus w0 into x2 gives me y2. w2 into x1 plus w1 into x2 plus w0 into x3 gives me y3, and so on. Now, this probably raises the question, why did I decide to draw the arrows in this particular way? Why did I decide to put x along the horizontal axis as vertical lines, the w's as horizontal lines along the vertical axis, and the y's as these diagonal lines which go towards the bottom right? This is not a unique way of doing it. This is one particular way by which you can represent the computations that are being performed over here. A more detailed explanation for how you could come up with this kind of computation by starting with the original equation for the graph has a lot of theory behind it. There is the whole theory of so-called regular iterative algorithms, which is briefly discussed in the textbook reference that I had mentioned, but is generally speaking too much detail for us to go into as part of this course over here. I'm going to focus on another part of the problem, which is assuming that I have constructed a dependence graph in some way as shown over here, how can I use this in order to map it onto a given architecture, and how do I explore different kinds of architectures that can be implemented in this way? So this structure that I have drawn over here is, in other words, called the dependence graph. And as you can see over here, it has a regular structure. What do I mean by a regular structure? The kind of computations or the nodes are all identical to each other, right? So each of these points marked with a black dot, I'm going to call a node or a computation. And because all the nodes in the graph are essentially performing the same computation, in other words, over here each node takes a weight and an input and multiplies the two together and propagates that value that it has generated in a certain direction, in this case towards the bottom right. Okay, that structure essentially tells us that this is the computation performed by a node, this is the data that it gets, and that this is the way it propagates its output. I can redraw an individual node by saying that it gets an input x, another input w, and it propagates an output y. Note the directions in which I have drawn each of these arrows. These are important, right? We can essentially think of the w as a vector, and the value of the vector I will consider to be 1, 0. Why is this? It basically has 1 along the horizontal axis and 0 along the vertical axis. Which means that the x corresponds to the vector 0, 1, and y corresponds to the vector 1 in the horizontal axis and -1 in the vertical axis. So effectively, the directions of propagation of each of these signals can be seen as 3 different directions: 1, 0 for the w's, 0, 1 for the x, and 1, -1 for the y's. Note that this dependence graph that I have drawn over here, although it captures all the possible outputs and so on, does not really have a notion of time associated with it. It's primarily focusing on just capturing all the computations and the dependencies between them. Right? In other words, we can think of this as being a graph purely in the spatial domain, that is the ij axis. And what we are interested in is to map from the ij axis to what we will call J prime and T axis, right? Where this T will now be time and the J prime will correspond to location or a physical position of a particular computation. Okay, so let's take this same example through, and we will use this in order to illustrate exactly what we mean when we, by saying that we are projecting from this two-dimensional ij axis to a one-dimensional j prime axis and a one-dimensional time axis. Mathematically, we are going to use the notation over here. We will basically discuss it in terms of projection in a vector space. Okay. Now, although this sounds complicated, I'm going to use this fairly simple example and hopefully work through it, and hopefully the basic ideas of what are being discussed will be sufficiently clear by the examples that we have taken. So first we will start with a couple of definitions. The first thing that we need is a so-called projection vector that I'll call D. Now, in terms of notation, since I'm writing this, it's difficult to easily indicate what are vectors and what are regular scalar values. So I will put an arrow on top in order to indicate that this is a vector. Right? This, in some cases, what happens later we will see is that the projection space, processor space vector that we will be using in this example might actually need to be represented as a processor space matrix instead. Right? In which case the arrow on top is not really the correct notation to use, but we will continue using that just for simplicity, since it makes it easy to draw what we are writing over here. The other thing that you will notice in the textbook is that they use the notation that a vector has to be a column vector. In other words, it has to have the value d1 and d2, which means that the transpose will have the value d1, d2 and will be a row vector. Again, I am not going to carefully distinguish between the two notations over here while writing it down, but please do be careful about this, because it does make a difference when you are actually implementing the matrix computations required for doing this. In the present instance, while writing on the notebook over here, it should be fairly clear from the context whether I mean a row vector or a column vector. Now, what exactly does this projection vector mean? Essentially, this projection vector says that two computational nodes in the dependence graph that are separated by D will be mapped to the same processor. In other words, if I have D or D transpose equal to 1, 0, that essentially corresponds to the vector looking like this. Implies that two nodes over here, let's say that this corresponded to the value 1, 0 and this corresponded to 2, 0, they will map to the same processor. In terms of the dependence graph that we have over here, you will notice that yes, there are quite a few such processor nodes that lie on the same horizontal line. How exactly do these map? What are the possible values of D that we can use? That's basically what we are going to look at in the examples that follow. Okay, so now that we have this projection vector, we can essentially define something called a processor space vector. And this processor space vector once again will have this value. It will be of the type P1, P2 in this case. And how it is defined is to say that any node x which has coordinates x1, x2 will be mapped to processor number given by P transpose into X. In other words, it will be given by the value P1 x1 plus P2 x2. So in other words, by computing the value P1 x1 plus P2 x2, we will exactly know what is the processor number on which a given functional node in the dependence graph needs to be mapped. Okay. Now, I'll just go ahead and define the next two terms as well before getting on to certain properties of these vectors that we have. The next term of interest to us is something called the scheduling vector. S, which is given once again by two components, S1, S2. And all that this says is any node X will be scheduled at the time T is equal to S transpose X, which is equal to S1 x1 plus S2 x2. And finally, there's one more term that I'll define over here called the hardware utilization efficiency. Which I will define as 1 over S transpose D, the magnitude of this value, right? For the time being, let's just leave this definition as it is. We'll come back shortly to why this definition works, why I would want to use it, and what exactly it means in practice. So now let's look at a few properties of these vectors that I have defined. Right? The processor space vector says that it gives you the ID number of the processor for a given computation. And the projection vector, on the other hand, says that two nodes separated by D must be on the same processor. So let's take 2 points in the computation, x1 and x2 are 2 points in the dependence graph. Where does x1 get mapped? This is going to be given by P transpose x1, and similarly the processor for x2 is going to be given by P transpose x2. What does the projection vector essentially say? These two must be the same, which means that I must have, let me clarify. These two must be the same if x2 minus x1 is equal to D. That is to say, if x1 and x2 are separated by D, then both the processors for x1 and x2 must be the same. So let's put this clearly. What we say is Pt x1 should be equal to Pt x2 if x1 minus x2 or x2 minus x1 or x1 minus x2 is equal to D. Either way, we don't care about the direction actually. In other words, P transpose into x1 minus x2 must be equal to 0, or put it another way, P transpose D must be equal to 0. This is a nice observation. Effectively what it's telling you is that the processor space is orthogonal to the projection vector. In terms of visualization, you can think of it this way. Effectively what we are saying is that I have some kind of a two-dimensional space, and I have a projection vector which basically lands me on a certain plane of projection, which is orthogonal to the projection vector. This is sort of a simple way of visualizing what exactly is implied by the term projection vector as well as the processor space. As far as we are concerned, the important point is this particular property, which states that the processor space is orthogonal to the projection vector. P transpose D must be equal to 0. There are two ways of looking at this. One is to say that I can always use this equation to verify whether my given choice of P transpose and P and D are valid. The other is to say that once I have chosen D, I can pretty much use this in order to compute possible values for P. Okay. What's the next property that we can find out that's of use to us? This regards the time of scheduling. If x1 and x2 are mapped to the same processor, what can we say about the times at which they can be scheduled? They cannot be possibly scheduled at exactly the same time. In other words, S transpose x1 cannot be equal to S transpose x2. Or rewriting this, S transpose x1 minus x2 is not equal to 0. Or another way of writing this would be S transpose D is not equal to 0. Now, if you go back and think about what is meant by hardware utilization, you will realize that S transpose D equals the time difference between successive computations on the same processor. If S transpose D is equal to 1, effectively what it says is a new computation is going to happen on that processor on every clock cycle, which in turn means 100% hardware utilization, which is exactly what we meant by saying that 1 over S transpose D is the hardware utilization efficiency. In other words, if for example S transpose D is equal to 2, it means that a new compute happens on only every alternate clock cycle, which essentially implies that 1/2 duty cycle of using the processor, which basically corresponds to a 50% hardware utilization efficiency. moving further from here, the last property that we are interested in is to think of what happens to an edge in our dependency graph. How do we handle an edge in the dependency graph? For example, if I had two compute nodes and there was an edge over here, E, this E essentially corresponds to an edge from, let's say, x1 to x2. And since we know that x1 will be mapped to P transpose x1 and x2 will be mapped to P transpose x2, what we can say over here is that the edge E will be mapped to P transpose E. That is to say, the P transpose E can be used in order to find out what would be the new direction of the resulting edge that we have. And similarly, S transpose E will give the number of delays on the resulting edge. Now, these definitions are a bit hard to understand in themselves. They are best explained by relating them clearly in context to a more specific example. The example, of course, that we have in the present case is the FIR filter. So what we will do is to go through the example of the FIR filter, take its dependence graph, take a few different examples of projection and scheduling vectors, and see what are the different architectures that result from doing this.